I'll show the screen. Cool. So hopefully everyone can see that. All right, so welcome to another OpenJ9 community call. In this call, we're going to be talking about the most recent releases, so the JDK21 release, that's 0.42, and the January quarterly release. So we're going to have a few presentations today just to highlight some of the changes that have gone in recently and how they impact users. Before we do that, I'll just quickly talk about some key dates. So we released JDK21 in this month. We are in the process of releasing the January quarterly update, so that may make it this month or early next month. And then JDK22 and the second quarterly update, I've put 44/5 because unclear as to what we will name it, but those two are planned for April. All right, so in terms of JDK21, this is the list of the JEPs. I won't go through each one, but the main one that went GA was visual threads, and that was one that required a lot of effort from the team, as well as with FFM. There were a lot of API updates, which also required a lot of effort from the developers. One to note is compared to this allow dynamic load of agents. So this now will output a warning if you don't explicitly turn on the option that enables dynamic loading agents. There's other things here, but those are kind of the key ones. Okay, so from a JDK perspective, I'm just going to go through a quick summary from high level. So OpenJ9 extract is removed from JDK21 and on. The reason for this is that in the Panama project, the groveler, the tool that's used to generate the native bindings is also called JExtract. So we've removed JExtract, and JPackCore, which is essentially the alias for this, is replacing it. As well, system GC behavior has changed. Historically, calling system GC on OpenJ9 has never been a guarantee that GC will occur. But with this change, calling system GC guarantees that GC occurs, and also guarantees that if there's anything in the finalized queue, that the finalizer also runs. The reason for this change is that there's a lot of tests that rely on this behavior, and so for consistency with the RI, we have gone ahead with this change. We've added thread allocation MXBean APIs as well. We also added a compatibility mode for Elasticsearch. Elasticsearch has requirements for hotspot with G1GC. It's hard-coded. So we've added a mode that essentially just provides the right information such that Elasticsearch is satisfied and continues to run. This has been tested on PowerPC and x86, and as far as I know, there have been no issues. We also added an option to retain JN IDs for async get call trace. The issue is that if a class gets unloaded and you don't retain IDs, then the agents, the profiling agents, essentially are holding on to corrupt data, which can cause crashes. So with this change, we essentially eliminate that scenario at the cost of using additional memory. We've also added a compatibility flag for CPU load so that it mirrors the behavior of the RI. From a Siri perspective, we've done some work on heap resizing and restore. So on restore, you can modify the heap. There are restrictions though, so you can only reduce it from the initial heap size. You cannot increase it beyond that. As well, we've added JVM portability mode. For the time being, this is mostly a JIT option. It forces the JIT to restore in a portable mode. And for the most part, we're using this as a debugging feature. We've added some time compensations for runtime MXBean so that it reflects more accurate time for get uptime. So it doesn't include the time where the JVM is in between the checkpoint and restore. We've also added concurrent hooks. This is in addition to the single thread hooks, so that users can run hooks alongside active Java threads. And lastly, there is a new option to toggle this CRU security providers. By default, only CRU security providers are allowed. But for some applications, if the required security providers don't have CRU support, then you get an exception because the default behavior is to not allow anything that isn't CRU safe. But for some applications and for experimental purposes, there is a need to just disable this and permit all security providers. So the option is great for this reason. All right, so yeah, this kind of gives you a brief summary from a higher level. We'll now go to presentations that do a more in-depth summary of the changes. So we'll go in the order that was in the planning channel. So we'll start with LAN.
Sure. I'm just gonna, well, let me share my screen and just quickly, it's just one slide. Can you see it?
Yeah, I can see it.
Okay, so just some major updates from Aquavit. So first of all, Aquavit will branch around 6 weeks before the Open JDK GA tag. That means if the changes that needs to be double delivered after that, just something to be aware of. For the CRU related changes, we have test pipeline support for the CRU on Z Linux. And then we're still working on the Z version detection in TKG, so we'll be able to actually control which microarchitecture we'll land on. And we added the CRU container based functional test, so that's already in the pipeline. Although they still have some problem that we're trying to sort out, but the basic pipeline is in. And SSL test, it's added. This is a test from the Red Hat, and this is added in the dev.functional. The plan in the future is going to move into Sanity or extended as a part of the Aquavit test suite. Also enable the verbose GC log in OpenJDK test. Couple of things for pipeline efficiency. So the third-party test libs are now pre-staged on the machine, except the system test. That one is the next we're going to work on. And also we only clone OpenJNI repo when we need it. So for example, if we run functional, then OpenJNI, we will git clone OpenJNI repo for its functional test, but any other test that's not needed, required repo, then we will not git clone. This is basically try to make sure the test pipeline will run faster. And then also updating the external test to remove some unnecessary checks. And then that's it from me. Any questions? No? Okay, back to you, Toby.
Thanks, Lan.
No problem.
We'll go over to the next one on the list, which I believe is Henry for a summary of changes.
Yes. Okay. Can you see my screen?
Yep.
Okay. All right. So just from a high level point of view, the changes that have gone in recently for the JIT compiler are in two broad categories: runtime performance improvements and, broadly speaking, ongoing defect fixes. So from in the category of the runtime improvements, some of the most interesting things for the new release are the addition of the XXI profile during startup phase options. So this gives explicit control to the user over whether profile information is going to be gathered during the JVM's startup phase for feeding into the JIT for optimization purposes. So previously, the choice of whether profile information would be gathered during startup relied on JVM's default heuristics. So it wasn't necessarily immediately obvious to the user whether profile information would be gathered at that point. So this gives explicit control to the user about whether profile data should be gathered particularly for trial runs of applications, so that the user has control over when that profile data is being gathered. If the options aren't specified, then it goes back to the default heuristics. There have also been some improvements to the ramp-up performance. So compilations that are happening early on during the application's run, the set of optimizations that happen at the default optimization levels, lower level optimization levels, have been narrowed down. So things that were taking a fair amount of compile time but not providing much benefit in terms of throughput at those lower optimization levels. So basically, this has the effect of reducing the amount of time spent compiling methods early on after JVM startup, but with little impact on the overall throughput of applications. And then finally, there have been some adjustments to the invocation counts required, the number of invocations of methods required before the JIT starts compiling those methods when the default shared classes cache is being used. So in previous releases, during the JVM startup, the invocation counts were set so that they favored compiling methods that are in the Java class library and would delay compiling application methods. But now the counts have been tuned to allow for the possibility of some more application methods to also begin being compiled earlier, which potentially reduces the amount of time spent running those methods in the interpreter. And that helps to improve the ramp up or execution time for short running applications in particular. So beyond that, I mentioned defect fixes. So there's always ongoing defect fixes going on in the JIT compiler. So I just highlighted a few here that are interesting, as they were especially interesting as user reported problems. So first one I've got here is an issue with system current time millis. That was an issue on Z architecture, where an optimization of that method was actually affecting the results that were being produced by it. So that's fixed in the noted pull request there. There's also an issue that was user reported with where in certain situations the JIT was potentially removing a check for integer divisions by 0. So that's been resolved. There was an interesting problem reported with where we were sometimes producing an exception from memory usage init when 1 GB pages were enabled. So that problem has been resolved. And an issue with some incorrect optimizations of loops that were going on. I don't have the details there, but if you want to read about the details, you can follow up in issue 17249. And those are the most interesting things for the JIT in the most recent release, in the current release. And that's it. Thanks.
Thanks, Henry. Cool. So we'll go ahead to, I'll see Jason here. We'll go to Alex and Dimitri for GC changes.
Yeah, hi. So I'll share my screen. Okay, so not really much of, or actually any standalone GC features that we worked on. It's if it's a which feature work, it was basically a combination of mostly VM features and some GC support like Instant On or Loom, and there are quite a few bug fixes, here and there. But some of the standalone GC features that we've been working for a while is of heap allocation for the bound GC, but that hasn't been released, so I'm basically skipping any changes that we are done there. Anyway, as a part of fixes, not much really visibility to the customers. I kind of singled out a couple of these, that are somewhat likely that a customer may encounter, because I think we saw them maybe more than once in different environments. And in general, just improving some GC behavior, like this one is related to excessive GC. In some cases, we would not report excessive GC, even excessive GC was still on. And this one improves somewhat heap consumption. In some cases, we would not reduce the heap size when we really should. Lots of other smaller fixes, or on both, I guess, OMR side, which does kind of get part of in the Java release, even those OMR changes, some verbose GC improvements, another also with GC related, so just additional information over there just to improve the user experience, As far as the, again, features, as I said, it's mostly VM specific features, some GC, I guess, support for it. Instant On is, I don't really know if it's a really GA'd or this is still experimental, but anyway, there's some changes. For example, we clear dead objects when we create checkpoints, so it's kind of security feature. There was lots of other work that went into for the Instant On before, I think, 43, and also, which is also in the head stream, but I did not make it for 433, like supporting for GC threading or heap resizing, So I'm not showing these changes, but the work was done in this kind of time frame, As far as the JDK21 specific changes and or features, again, Loom is on, right? And we have done lots of work, but specifically just for 43, I think we had only like a fix or two, and I just showing one of them. Really, the other things are just some very specific changes that are not really likely to be encountered by a customer, and I'm not really don't want to go into any details, unless somebody has some kind of questions here. So that's it from me, basically.
All right. Thanks, Alex. We'll go to Jack and Babneet for Loom changes.
Toby, can you hear me?
Yep.
Okay, let me share my screen. Can you see the screen?
Yeah, I can see it.
Okay. So for Project Loom, there are three JEPs which are important. The first one is JEP 444 virtual threads. As Toby mentioned, this has been GA'd in JDK21, and it provides lightweight threads which have better performance than our normal threads. JEP446 scope values is another JEP, and this allows values to be passed implicitly to virtual threads. And this can be compared to thread local variables, but thread local variables won't scale as well for virtual threads, because virtual threads can be in millions. So they have added scope values so that values can be passed implicitly to virtual threads. And the last one is JEP453, which is structured concurrency. And in this JEP, what they do is they group a set of relatable tasks together, which are running in different threads, and they consider them as a single unit of work. And this helps them to streamline error handling and cancellation further. It helps improving reliability and enhancing observability. So in JDK21, we ended up adding support for all three JEPs. It was a combined effort from VM, GC, and JIT teams. I've also added links to the three JEPs. So if anyone wants to look at the specific implementation or the Java code samples, they can go through those links and explore those JEPs in more detail. Key changes were mostly performance because these JEPs pre-existed since JDK19, and we have been iteratively working on them. So in JDK21, the key performance changes were related to improved management of virtual threads, and a lot of effort for this went through the GC team. Then we optimized fast paths by reducing synchronization overhead. This was related to mostly how we linked JVMTI to introspect or inspect the virtual threads while they were running. And then we added another optimization, which is tunable through options, which is caching of virtual thread Java stacks. This helps in improving performance in cases where we have million virtual threads running concurrently. And then we also ended up parallelizing JIT code cache reclaim code. So this was moved into the GC, and the work for reclaiming was distributed among the GC workers. And previously it was done single-threadedly, which showed regression in few virtual thread workloads in comparison to the reference implementation, and parallelizing it gave us performance improvements. The next 2 points, which are performance tuning options, some of them are related to the features mentioned above, and then how we can better debug virtual threads. I will pass it to Jack.
Thanks, Pepin. So for JDK21, we've added 2 performance-related options to tune the specific application setup. First one is a runtime option, which is XX continuation cache. This allows the application to set a custom cache size instead of the default cache that is being set. So for default, we've opted for first layer with a single cache entry, and second layer with the number of CPUs on the machine size for the cache entries. For users where the application have a different allocation patterns and consistent like allocate and deallocate, when they have a bulk allocation and bulk deallocation, increasing the cache size would have a significant performance benefit, as the VM wouldn't have to do as much allocation and deallocation. Instead, we'll be able to use the cache more effectively. There's also a compile time option to track the profiling data for the continuation classes, which is the underlying support implementation for virtual threads. This option would record the cache statistics and log them to console at the VM exit point. It will include hit rate, total allocation, average allocation time, etc. This helps user to decide what is bottlenecking their performance on virtual threads. This can also help you to make decisions on what the T1 and T2 cache size would be for the runtime option. So next slide, please. For debugging, there's also two options added. One is to support RI's trace pin threads option. This would log whenever a virtual thread tries to yield, but wouldn't be able to yield due to being pinned, which is one of three cases. Either the user deliberately pinned it, or if it was holding a monitor, or in the last case, when it was entering a native call stack. This would help to identify any performance issues with the application, or if there's any race conditions where there's virtual threads that are taking forever to complete while others are not being executed in time. It also helps to identify starvation issues related to virtual threads. And the last option that was added for 043 was the show unmounted thread stacks. This would include all the unmounted threads which are not currently executing in the Java core file when a core dump is being generated. So to elaborate on what an unmounted thread is, in virtual thread, the system scheduler would allocate a bunch of carrier threads that are supposed to be a placeholder that would actually execute the virtual thread that are allocated by the users. Whenever a virtual thread is being started, it will unmount the carrier thread, instead mount the virtual thread onto the carrier's OS thread and execute from there. At that time, the carrier thread will become an unmounted thread and not show up in any of the thread traces in Java core. And using the show unmounted thread stack, it will forces the unmounted thread to also be displayed in the Java core. And when a virtual thread yielded, it will unmount itself, which means once a yield have completed, the virtual thread would also be considered an unmounted thread. So if you need to look at the Java stack for those ones, you would also need to specify the option to show those in the Java core file. Next slide, please. Yeah, so that's it, and we'll open it to any questions.
Yeah, just a quick question. So in slide 4,
Yeah.
maybe for those who are not familiar with the continuation caches, sorry, can you please explain the difference between T1 and T2?
Okay, so for continuation caches, T1 basically means thread local, where we have just one thread accessing it, and there will be no contention and no locking required on this one. For T2, it is a shared cache pool between all threads currently. This one is non-blocking, but it do have synchronization related to different threads, which we use atomic operations to guard the in-queue and dequeuing operation into the T2 cache.
Okay.
I guess more on performance is that increasing the size of T1 would help more in terms of performance, but it would not consider the imbalance in loading between different threads.
Yeah, thanks, Jack. Any questions from anyone else? All right. If not, thank you, Bami and Jack. And we'll go on to Cheng for foreign function APIs. And
Toby, can you hear me?
yeah.
Let me share my screen. So let's see what happens in the survey preview of FFI in JDK21. I just list everything, including JDK21, that user may should be pay attention to in their applications. So from Vim perspective, I recover the unit support and the downcode the linker options for your live functions. the rest of the stuff is already covered in OpenJDK and Java21. So I will explain a little bit later about what it means to the users. Unit support in Java21. This is not explicitly mentioned in the third preview. It's just fully implemented in Java21. So from my perspective, we are first supported in terms of downcall and upcall. So from user, actually there's too much difference as compared to the structure layout. Everything is the only thing user have to mention is that to make sure you have use the correct layout when it's coding in the programs, because if you use a wrong layout, they probably end up with some unexpected results when you do the downcall or the upcall in your code. So there's the rest of the code changes structures should be pretty much the same. I didn't see any bunch of difference in there. Memory management in Arena. Actually, if you have notes anything about what happens in Java 20, you see that there are quite a bunch of allocating functions in terms of allocating native or something else here or there scattered in Java 20, and which cause quite a lot of confusion from user perspective. So in Java 20, when you try to consolidate this allocation functions into the Arena to make sure to give the user to have a better clear understanding of what happens out there and unify everything's memory management APIs to Arena and segment allocators. So that means the user don't have to struggle and think about what should be used when they allocate native memories. So this is very easy to do and quite simplified in terms of the native memory allocations. And another things I didn't mention it here is about life cycle. So from Arena, so everything becomes very simplified, and they have to change the naming to make sure users understand what happens out there. Address layout. This is a new layout introduced Java 21 to give a user to handle how to locate address in their code. So I just let's grab a typical example from the Java 21 documentation. So if you, in terms of when you have to access a little bit complex structures like a pointer or rectangle, something else, something like that, and if you try to access a native nested structure, if there's a couple elements, you have to specify something like a difference element to locate the element. So in which case they have give users an easy way to access these elements in this point. It's trivial. This is actually new APIs provided in Java 21 for show live functions. What it means to show live functions? It means they probably runs very fast, returns very quickly, and probably there's something like n options or very basic arithmetic calculations out there. User don't have to expect it spend too long time in the functions. Otherwise, you will kind of destroy everything. So for perspective, so that means user have to think about how this affect their performance when you write their code if you try to use these APIs. Unfortunately, volleys has been removed from Java 21, and there's no plan to get them back because actually the tooling what happens is there are toolings F5 G extracts is not fully ready to deal with whitelist, especially for some platforms. So if you try to still run user whitelist, better try the early versions to see how it works. Fallback native linker. This is something also introduced in Java 21 to give the user to try to see what happens in the new architectures if there's no FFI support. So this actually what happens is there's provide an easy way to see how it runs the linkers based on the libfy and the certified open source project. So to see how to invoke the native functions. This is actually is internal implements, so totally invisible to users. The user can use this way to understand how it works with the libfy or with the F5, and try to, if you want to port into new platforms, you can refer to it and to implement everything in there. Yeah, that's about everything on my side. Back to Toby. Any questions?
Yeah, I'll just open it to the floor for questions, if there are any.
Sure.
All right. It doesn't seem like there are, so thank you, Cheng, for that.
Thank you.
All right, so yeah, this concludes our presentations for the JDK21 and January quarterly release. So thanks everyone for presenting. Thanks everyone for attending. And yeah, we'll do this again in April for the next set of releases. All right, so thanks everyone, and we'll meet again next time.
Thank you. Bye.